Lesson 5, Part 2. This is where we left off. This is an important lesson on statistical significance, so pay attention. Sometimes students get tripped up. If you get tripped up, make sure to do a little bit of independent reading on statistical significance. You can also feel free to set up a Skype appointment with me. So, the question becomes, in quantitative research, the question becomes, in many cases, are two numbers, or three numbers, whatever, different, really different from one another, right? So in this example that we looked at, 10.9 and 10.7. See, you're always going to end up comparing something, right? Is 10.9 different from 10.7? Well, you might say, well, of course they're different. They're two different numbers. 10.9 is different from 10.7. But remember, most of the time, almost all of the time, we are sampling. We're not taking a census. Remember, a census is when we examine every item in a population. If we examine every item in a population and then we get a difference between two numbers, then we know they're different and nothing further is required. We don't need to do any statistical significance tests. For example, if we were to ask every single American about their approval or lack thereof for the president, we could just ask them a simple question. Do you approve of the performance of the president? Yes or no? If we asked every single American, all 330 million Americans, and it came out as, let's say, 51% said yes, they approve, and 49% did not approve. We have done what? We've taken a census. We have not sampled. We took a census. We asked every single American. We asked every member of the population. Remember, a census is examining every item or member in a population. Okay? So we don't need, in this case, to do a statistical significance test. 51% is different from 49%. The two numbers are different. We took a census. Nothing further is required. But when we take a sample, we have to do a statistical significance test to find out if these two numbers are really different. And the reason is, remember we talked about when you take a sample, there's always just a little bit of error, right? So you have to basically conduct a test to find out whether or not two numbers, like in this example, 10.9 and 10.7, or in the example that I just gave, 51% and 49%, assuming we had taken a sample, right? We'd have to find out if those two numbers are different, because let's say you take it now. Let's do the same example on approval rating for President Obama. Now, instead of asking every single American, you took a random sample of 5,000 Americans, okay? And you come up with, let's just say you come up with 50.5% approve of the president's performance and 49.5% disapprove. So 50.5 to 49.5, a difference of 1%. But you took a sample. Are those numbers really different? You have to do a test, a statistical significance test. It's essentially a formula that informs you whether or not, if you were to continue to do this study, you'd get the same result. It might be that the difference that you found is just a product of the sample. It's just chance. In other words, maybe you do the same study tomorrow, you ask 5,000 Americans their opinions of the president, and now instead of 50.5% to 49.5%, now it's 50-50. What happened? Well, different sample. There's always that little variation, right? So you have to test to find out whether or not two numbers are different. And what we do is we plug. Basically, I'm not going to ask you in this class to actually learn how to, plug numbers into formulas and understand the formulas. You can do that in a stats class, okay, in a statistics class. But what I do want you to know is, once you plug the numbers into the formula, right? You plug the 50 and the 49 or whatever, and the sample size and everything into a formula, it's going to spit out a number. And I do want you to understand how to interpret this number. It's going to spit out for you a number called the p-value, or the probability value. The p-value, or the probability value. And it's going to look like this number here, 0.05. Maybe it'd be 0.06. Maybe you'll get 0.10. It'll say p equals something. Maybe 0.30. But the magic number for us that we want to see is 0.05. What does that number represent? It represents the probability value. 0.05 is what? Is 5%. 0.10 is 10%. If you think back to your, to math, right? 0.20 is 20%. 0.50 is 50%, right? So 0.05 is 5%. What this means, if it says P equals 0.05, pay attention, that means that there is a 5% chance that the observed difference between 10.9 and 10.7, or 50.5 and 49.5, or whatever, that the difference that you observe between these two numbers is just a product of the sample, is just due to chance. In other words, there's only a small chance, 5%, that the difference is just random. It's just due to chance. It's just due to the sample. That means there's a great chance, like 95% chance, that just the opposite is true, that the observed difference is not due to chance. In other words, there's a real difference. We're confident that there's a real difference. So some people get confused by that. The lower the p-value, the more confident that we are that there is a difference. Okay? So for example, let's say I want to do a survey, or let's say I want to do a content analysis of CNN and Fox News to find out which network was more sympathetic to the police during the Michael Brown protest period. Okay, and I do a number of different analyses, blah 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 blah, and I find out that 52% of the reports, the TV reports, 52% of the TV reports on Fox News, they were sympathetic to the police. I'm just making this up, obviously. And on CNN, they were sympathetic to the police 30% of the time, in 30% of the reports. 52 and 30, you might say, well, that's a huge difference. You still have to do the test. Now, in all likelihood, in this particular example, if you had assuming you had a large enough sample, I guarantee you'd have a p-value of less than 0.05. But you still have to do the test. So you do the test, and this is all done, by the way, by statistical package. I mean, there are statistical programs on your computer. Nobody does these by hand anymore. I mean, if you take a stats class, you will have to, but like me, you'll take the stats class, you'll be really good at doing it for about a month, and then you'll forget about it, and then you'll let the computer do it for the rest. I couldn't do it right now if my life depended on it, frankly. But the computer does it, so that's fine with me. So anyways, what did I say now? 52% favorable to the police in Fox News, 30% favorable on CNN. So you do the study, you do your little statistical significance test, it spits out a p-value. The p-value is 0.01. What does that mean? If we were in class right now, I'd let you think about it, I'd let you ponder it, and I'd field some responses from the students. So think about it for a second. What do you think? Try to answer the question right now. You can pause this video. That's the nice thing about video. You can pause it. Think about it. What does that mean? The p-value is 0.01. What does that mean? It means that there's a real difference. That there is this, that what we would say in the paper is there is a statistically significant difference between the two numbers, and how Fox News and CNN, in this made up example, talked about the police and their degree of sympathy toward the police. Okay, 0.01 is less than 0.05. 0.05 or less, thumbs up. There's a difference. That means, in this example, that means there's only a 1% chance that the differences that we observed were due to chance. But there's a 99% chance that the differences are real. In other words, think about it like this. If you did this same study with the same sample 100 times, you'd get the same result. A difference between Fox News and CNN, pretty big difference at that, 99 times out of 100. Just one time it would turn out to be different because there's always random error, right? So in other words, in that example, you could be really confident that there's a difference. One more example. Let's say you're doing an experiment to find out if a certain video game makes people more aggressive. So you have two groups of people that play the video game and people that don't play it. People that probably play some other video game that's not as violent or not as action-oriented or whatever. So again, you're going to have this comparison. And that's what you get. In quantitative research, you're always going to have a comparison at some level. So you do your little comparison in your two groups, and you have a little scale measure that you use, and you end up finding out that, I'm just making this up, but you end up finding out that the people that played the violent video game, or the more action-packed video game, scored a 4.3 on some aggression scale that you developed, right? I'm just making it up. But that's how you'd have to do the study, right? You'd have to have some scale by which to measure these people. And the people that played the other game or that didn't play a game at all scored 2.7 on the aggression scale. And of course, these two groups would have been the same going in. You'd know that they were exactly the same as one another. They were homogeneous going into the study. And I'll explain later when we talk about experiments how you can guarantee that the groups are the same. But anyways, that's neither here nor there right now. So you found a difference, right? 4.3 versus, what did I say, 2.9? Is it a real difference or not? We have to do a test. We've got to do the statistical. Anytime you're doing an experiment, you've got to do a statistical significance test. When you do a survey, pretty much all the time you're going to have to do a statistical significance test unless you take a census. Same thing with the content analysis. Unless you're taking a census, you've got to do a statistical significance test. And there are different kinds of tests, and we'll learn about them later. But let's say you do this example, you do the statistical significance test, and it comes out as 0.001. That means there's like no chance that these differences are due to chance. In other words, that's a really powerful difference. These results, we would say in the research paper, the differences that were found were statistically significant. There were statistically significant differences between those who played the game and those who played the other game or didn't play a game or whatever. Okay? 0.001, that's what? 1 out of 10,000, right? If my math is correct, right? 0.01 would be 1 in 100. No, 0.001 would be 1 in 1,000. Sorry. So 0.001 would be, there's just a 1 in 1,000 chance that these differences are due to chance alone, that they're just a product of the sample. In other words, you can be very confident that there's a difference. If the p-value ends up, let's say you do another study and the p-value is 0.26, what's that? 0.26, is it higher? Is that greater than 0.05 or less than 0.05? 0.26 is greater than 0.05, so no statistically significant difference. Okay? If you have any questions on that, let me know. This is just an example of a content analysis. I'm going to go through this really quickly, but you can read it on your own. You can even look up this study on Google Scholar. Greenberg et al., Greenberg and colleagues, et al. Means and colleagues, from back in 2003. They were studying obesity on TV programs. This is, one of the things that you could use content analysis for. This is an interesting study. It's important to know how obese characters are portrayed on TV. What if they're portrayed really negatively? Wouldn't we want to know that? Maybe they're working to, maybe unintentionally, of course, but they're maybe they're going to end up lowering the self-esteem of obese people in society. So we want to know how they're portrayed on TV. So they did a content analysis. Sorry, I got an ice cube in my mouth by mistake, taking a sip of my water. These are just some shows. Just kind of as an interesting aside, one actress here is in 2 shows. Can you spot who it is? Well, you probably can. Not like this is very complicated. You can see it all. But the blonde in the upper left there, on Scrubs, her name is Sarah something. I forget her name, but she was also on Roseanne in the bottom right. Bet you didn't know that, or maybe you did. Anyways, you can see most people on TV are skinny. There are some exceptions. Roseanne is an exception. That was a show back in the day before before your time in most of your cases. Maybe you've seen some reruns, but the main characters on that show, Roseanne Barr and what's the guy's name? I forget his name. Her husband on the show. They were obese characters. So that was kind of different, kind of in a way groundbreaking, right? For a primetime show. So what did they do? First thing you got to do is take a sample. They took their sample. They were doing this study back in around 1999. So they looked at shows in 1999. They took a really strong, robust sample. I mean, this is huge. 60 TV shows on all 6 of the major networks: ABC, NBC, CBS, Fox, UPN, and the WB, I think, were at that time, right? So you have 60 programs, right, from the 6 major networks, 10 shows from each of the major networks. It ended up being a total of 275 episodes, selected at random, of course, 210 hours of programming. Because some of the shows are an hour long, some of them are a half hour long, right? And they looked at comedies, dramas, everything. Then they've got to design a coding sheet, and they looked to code a number of different things. They were coding the characters, obviously their body type. I mean, that you have to code the body type. Is the person skinny or obese, right? Medium sized. They did that. But then they coded for the person's race, their gender, their mood, social interactions, like what were they doing, their behaviors, sexual behaviors, did they have a romantic interest, were they happy, were they sad, all these different things. And you have to note the operational definition. Remember we talked about that? How do you define a certain concept? How are you going to measure a particular concept? That's important to know. Because some people don't realize there have been all these studies of obesity, right? On TV or whatever. And you'll get one study will show, oh, obese characters are portrayed, or it'll say 10% of the characters on TV are obese. And then you see another study done around the same time, and it says 3% of the characters are obese. Why is that? It's because they operationally defined, these 2 different researchers operationally defined obesity differently. You have to look at the operational definition. And you have to take operational definitions seriously when you're doing research. In other words, how are you going to measure this concept? How are you going to measure obesity? How are you going to define it? I think what they did, it's been a while since I read this study, I think what they did is They used some medical association where they had like cutoffs for certain weights, basically. Like, for a woman, it might be above, I don't know, 180 pounds is obese. I don't even know. Something like that. For a man, maybe 230 pounds is obese. Whatever it was, they use that. But then now they can't go and weigh the characters from Friends, right? But what they can do is there are these approximations that they can use using visual imagery where you can kind of tell how you can sort of estimate pretty accurately how tall someone is and how much they weigh based on looking at them in different positions. So that's probably what they did, and they probably showed their coders different examples. Okay, this is what we mean by thin. This is what we mean by obese. This is what we mean by average or medium. That's what they did. But the point, I'm stopping now because I want you to think about operational definitions. How are you going to measure? On this exam that we have next week, I might say, hey, here's a concept. How would you measure this concept in a particular study? If you did a survey and I said, how would you measure gender in a survey? Think about that for a second. How would you operationally define gender in a survey study? That'd be pretty easy. If I asked you that on a test, you would just say, I would just have a question, and I would ask them, are you a male or a female? And I'd have two options, male and female. That's a pretty easy one, right? But it gets more complicated with like mood. How are you going to measure mood? How do you know anger when you see it? It might be something like, well, if a person yells, if they become visibly angry with an angry facial expression, like a scowl, that would count as anger. I'm just making this up, but it's up to you. But you have to figure out how you're going to measure these things. So this is what they were looking at. Here are the results. You can read through these yourself. It's kind of interesting. Whereas 1 in 4 women in reality, they did these inter-reality comparisons, which are always very interesting. 1 in 4 women in reality are obese. On TV, it was 3%. Only 3% of women on TV, the characters in 1999, were obese, compared to 25% in real life. Whereas 5% of women in reality are underweight, a third of the women on television were underweight. So there's a lot of neglect of obese people, and there's a lot of overrepresentation of skinny people on TV. That's one basic finding. They found that African American characters had larger body types than white characters. They found that married characters were larger than unmarried characters. Unemployed men were larger than employed men. Body size increased with age. They found that larger characters had fewer romantic interactions. They found that larger characters had more negative interactions. Larger characters weren't as helpful. They were less likely to be leaders, and so on and so forth. So they found a negative portrayal, essentially, of obese people on TV programs. They're not portrayed positively or realistically, and that's, arguably a very serious problem. If we were in class right now, I'd have you design a content analysis. My advice for you before the exam is design a content analysis. Like, come up with a topic and come up with a hypothesis and come up with a sample. Like, I'm going to study, this is the time period, this is my sample, this is the content I'm going to examine, this is how I'm going to select units, this is my unit of analysis, remember that? Then I'm going to look at, then I'm going to design a coding sheet, right? Who knows? You never know when that might come up on an exam, having to design a coding sheet.